Howdy, chem fans! It is time to take a look at day 75 and a thing called the Haber process. The basic idea is to be able to describe what the Haber process is, how it connects to this thing called equilibrium we've been studying, and how it impacted world history. Not that this has anything to do with real life, it's just chemistry. Well, anyways, we'll see today. If we look at this, of course, you can see that in the springtime, especially if you go up north here, you will see those wonderful tulip and daffodils blooming like crazy. Oh, man. And not to mention those beautiful roadies that are right behind there, Finny boy. Wonder what's going on there. Can't be chemistry. Here's what I want to know today. I've got a simple reaction. It's the formation of ammonia. You can see I've given you the reaction equation right there. I want you to predict what will happen if I make all those changes. That should be a piece of cake by now. Then the hard part. I want you to draw and explain why the forward reaction is exothermic but has a low KEQ. Now, by now, that should not be like a mysterious language. That should start to make sense by now. So, pause me. Write down the questions. Try to answer them on your own. Make sure that you draw and explain, because that helps your brain. Cool, let's tackle this one together. If we look at the first one, first thing you want to think about always, of course, is energy. So if we draw a simple idea here, we've got this thing called an energy diagram, right? And with that energy diagram, we can see that heat is a product here, which means that our forward reaction is exothermic, right? That would mean the reverse reaction is endothermic. So if I look at this simple diagram, it's going to be a downhill battle from reactants to products. Always think about energy first. Then I asked you to predict what will happen if you do the following. Well, these are my reactants. These are my products. So what's going to happen if I add nitrogen? Nitrogen is a reactant. And Le Chatelier's principle basically says that if you add, it moves away, right? So this is going to help to shift it to the right. And that's because you're going to have more nitrogen collisions. But it's not going to make a whole lot of ammonia. And I want to make a ton of ammonia. A ton of ammonia. As much as humanly possible, right? But let's try another trick, right? We're going to add this stuff called hydrogen. And when we add the hydrogen, hey, it's a reactant. It's going to shift to make more ammonia. But once again, bummer, it's not going to make a whole lot of ammonia. Just a little bit, not a lot. I don't have to write home about, right? Then we're going to try another trick. Let's try increasing the heat. Well, if we think simply, we can think of heat as a product. So if I add product, it should move away from it. So this actually will not make more ammonia for you. This will destroy ammonia. And if we look at this, that means that it's not doing what we want. We want to make ammonia. I want to make lots of ammonia, right? So what if we increase the pressure of the system? Well, that'll favor whichever side has less particles. And we can see this side has, well, there's one there and there's three there. That's 4 particles. And this only has 2 particles of gas. So that's going to, once again, shift to make more ammonia because it has less particles for less collisions. You try to make more collisions. But here's the problem. It's not going to make much ammonia at room temperature, 25 degrees Celsius, because it's too cold for the reaction. But if you heat it up, you'll destroy ammonia. So doesn't really work, right? Okay, one more trick. Le Chatelier said, if you add, it moves towards, or it moves away. But if you take, it moves towards. So if we look at this, I'm going to remove ammonia, right? And that's cool because that's going to take ammonia out. So now it's out of the way. So things like the nitrogen and the hydrogen are more likely to collide. That will cause it to shift and make more ammonia because now the ammonia is not in the way. They can collide the reactants. But once again, it's not going to make much ammonia, and it's going to be too hard to separate out. So you can make a little more ammonia, but not lots, and I want to make lots of ammonia, right? Why is that? Well, if we look at this, it all has to do with this thing of what kind of reaction it is. So if we draw this, the first thing we should recognize is we need to explain why this has a low KEQ and why the forward reaction is exothermic. So first thing I should do is remember that these are molecules, right? And there's a whole lot of nitrogen and hydrogen there, so I can use this handy tool called Conc. Conc, if you say it right. And Honc's great because it tells you the number of bonds each of these can make. And there I've got, 3 bonds for nitrogen, 1 for hydrogen, 4 for carbon. Oxygen's got its 2. That tells you what it takes to make them happy, right? So let's try that out. We're going to use this nitrogen stuff. It's N2, so that's 2 nitrogens, and those 2 nitrogens are going to be bonded together. When they're bonded together, they got to have the right number of bonds. So the only way that I can do that is each of those nitrogen would start off with its 5 electrons that it had on its own in its valence shell. But each of them needs 5, so what they're going to end up doing is they're going to end up forming a weird bond that's new to us called a triple bond. And in a triple bond, what they're doing is they're in a tug of war, but they're fighting over 3 pairs of electrons. Now, just looking at that right there, if you imagine something like a single bond is 1 set of hands holding, and you imagine a double bond is 2 sets of hands holding, the triple bond's like 2 hands and 1 foot, right? Which means that that's a lot of things holding these 2 things together. That triple bond is, very, very stable. It's hard to break, right? And if it's hard to break, that's a crucial thing. If it's hard to break, that means that nitrogen gas is not very reactive. And not being reactive means that you're not going to break a lot of it to make ammonia. Oh, that's why this reaction has a low KEQ. It doesn't like to make product, right? It likes to stay as reactant. It's not very productive. And that's all because of that triple bond in nitrogen gas is so stable. Now, that is a good thing because, 70%-ish of our atmosphere is nitrogen gas. And if it was reactive, then every time you lit a match, we'd all catch on fire and die. So it's good that nitrogen's not reactive, unless you want to make ammonia, right? Now, I want to react that with this stuff called hydrogen gas, so I'm going to throw in some hydrogen gases, right? And with those hydrogen gases, they are happy with a single bond, so that's going to give them 1 electron each that they're sharing back and forth for 2. Hey, they're both happy, right? Now, they're fighting over those things, and they're directly in between them. You can see these electrons are also as far away from the nucleus as possible. These are covalent molecules, right? These are covalent bonds, and these are non-polar covalent because they're sharing equally. They're in a fight with their own kind. Think back to the tug of war we did at the beginning of the year, right? But there's not 1 hydrogen, there's actually 3 of them, and hydrogen gases. And each one of those, of course, is sharing a pair of electrons. They're all in a fight together, and they're easier to break. I mean, hydrogen gas we've had fun with, boop, it burns, and you can combust it because, of course, it's easy to break a single bond. But I want to take these, and I want to slam them together. And that's what the arrow is showing us, is that we have a collision and a change, right? Now, if I collide those things together, they go from being the stuff called nitrogen gas, and they become the stuff called ammonia gas, right? Now, the ammonia, of course, if you look at Conc, nitrogen needs 3 bonds, hydrogen needs 1 bond. So that's why you can set it up in that beautiful trigonal pyramidal, right? And when it does that, there's going to be an unshared pair that's going to push down on those. But the key thing is, if we think about electronegativity, who's the bigger hog here? Who's got more pull? That's the nitrogen. And the nitrogen is going to pull those electrons closer to it. It's not going to rip them off. It's not strong enough to do that. But when it pulls them closer to it, it ends up hogging the electrons because it's more electronegative. Now, when it does that, those electrons now drop closer to its nucleus, and that stabilizes those electrons. I wouldn't, of course, make 1. I would make 2 of these. So I got to draw both of them because, law of conservation of matter. And when I do that, it's the same case. So all those electrons are being pulled closer to that nitrogen. So now they're sharing them, but they're sharing them unequally. This is on the order of a polar covalent bond, unequal sharing. In addition to that, my other product is this stuff called heat energy, right? We figured out why there's a low KQ, but we got to figure out why it's exothermic. We know it's exothermic because it's giving off heat, but where's the heat coming from? Well, that all goes back to what we don't ever draw in our reactions, which is a shame. That's the transition zone, and that's what's going on in this collision, right? If they collide just right, you can see that there are a bunch of hydrogens, and each of those hydrogens, they've got electrons that are far away from their nucleus. They're high in potential energy. They're far in their distance. That's why, they have energy, the potential to fall closer to a nucleus. When I give them somebody like nitrogen, which has more electronegativity, more pull in its nucleus, well, if they slam them into each other just right with the amount of energy, that electron will pop off and drop down to a lower energy level closer to a nucleus on the nitrogen. Now, crucially, this looks an awful lot like an energy diagram, doesn't it? It's like they're going from a position on hydrogen to a position on nitrogen. Oh, that's what we're talking about here. As they do that, of course, they're going to lose a lot of energy, and that's going to come off and be released. And it's released as the easiest forms to make. It comes off as heat energy and light energy, right? Electrons falling represents, the light that we see, or creates the light that we see, the photons. So if we look at this, the electrons are falling closer to the nucleus of the nitrogen, and that gives off the extra energy. And if it's giving off energy, that's exothermic. So that's why this reaction is, of course, a low KEQ. It doesn't like to make product because nitrogen's so stable. And it's exothermic. It's a downhill battle because, of course, the electrons are dropping to a lower position closer to the nitrogen, right? Now, why does that matter? Why would anybody care that, yeah, okay, it doesn't like to make ammonia, but it gives off heat? Well, crucially, we would try to figure that out in a class. Why would you want to make so much stinky ammonia in the first place, and why is it such a bummer that it's hard to make? What do you use ammonia for? Well, if you're humans, you recognize that ammonia helps make these things called fertilizers. Plants love fertilizers, and we like food. The other thing it's very good at making, of course, is if you can make things like ammonia, then you can make nitrates for not only fertilizers, but explosives. Oh, other things that humans really like, right? So if we dig into this, one thing that we should recognize is in the past, if we wanted to grow a whole bunch of flowers like this, right, we would need tons of fertilizer. And unfortunately, ammonia is pretty rare in the environment, except for a couple places. In the old days, if they wanted it, they'd have to go all the way from Europe down to this place in South America called Chile, where there's a whole bunch of birds that have been eating fish life for a long time and pooping. They make these big guano pets. And the guano, the bird poop that's all over the coast that's there, well, that makes the caliche mines. And they would go in and they would dig up the bird poop for the, of course, ammonia that's there. And then they ship it all the way back across the world on the sea, making it very expensive because it's rare and far away. And that meant that growing food was still really expensive. So this was reserved for, those that could afford it. The theory was, okay, well, this is kind of annoying. We understand chemistry now. Why don't we just try to synthesize ammonia from the nitrogen in the air and the hydrogen that we can get from things like oil or water if we get it pretty easily by doing those things, by breaking it apart. And that's where, of course, it came into the challenge of this has a very small KEQ. It doesn't like to make ammonia because nitrogen's so stable. So the challenge became to increase the KEQ to get the reaction to do what we want, to make more ammonia so we could have more fertilizer. And, well, the guy that figured that out was a guy named Fritz Haber. And if we look at him, he came up with what's called the Haber process. You also see it as the Haber-Bosch process because he worked with Bosch as well. He's born in Germany in the late 1800s. Most of his work's in the 1800s and then in the early 1900s. And he figures out this thing called the Haber process where he found a way to increase the KEQ and produce more ammonia. And he did it by using a bunch of Le Chatelier's tricks. He used high temperature, high pressure, a catalyst, and he took out the ammonia. And for that, he won the Nobel Prize for Chemistry in 1918. Ironic year. 1918. I wonder what was going on then. Now, if we look at his process, this is his setup, and it looks really, really fancy. But the idea of it is elegantly simple. He knew that he had to have some nitrogen, some hydrogen, and some ammonia, so he pumped in the nitrogen and hydrogen. And when he did that, what he did was he pumped in a bunch of it, so they would collide more and make more reactants. So he increased the amount of nitrogen and hydrogen. Then inside of here, he increased the temperature so they would hit more often. The only problem is that that would also destroy some of the ammonia he made. But he was tricky. He figured out he could make it easier for them to get over that activation hump by reducing the activation energy by adding a catalyst. And the catalyst he came upon was rust, iron oxide. Now with that, it put it in the right position so it was easier for the nitrogen and the hydrogen to run into each other. And when they did that, they made ammonia. And then he didn't want the ammonia to get destroyed by the high temperature and the high pressure of forcing these things together, but it was the temperature of the problem. So what he would do is he would then funnel it off to another side, and he would actually take away the heat. And when he did that, he put it into a condenser. And the condensation point, the point at which it becomes a liquid for ammonia, is lower than it is for nitrogen and hydrogen. So he could condense the ammonia off and then pull it out. Hey, he was taking away the ammonia, and that caused it to then recycle back the nitrogen and hydrogen, and he could use that to make more ammonia. So he used all of the Chatelier's principles, increasing the reactants, decreasing the products, increasing the heat to get more collisions, and of course increasing the pressure so that he could produce more of the thing that there's less particles on, the ammonia, the product. And he also got sneaky and used a catalyst to reduce the activation energy. Genius! No wonder he won the Nobel Prize. Now, cool thing about this, before the Haber process came along, right, the human population was really, really low because there wasn't enough food to feed people, and fertilizers was pretty rare, so you couldn't grow a lot of food. So people starved and stuff, right? Even Darwin wrote about that. Then Haber comes along, and he comes up with his Haber-Bosch process. And when he does that, suddenly there's tons of fertilizer so they can grow more food. And look what the world population does. It skyrockets because there's more food, especially in this place called Europe where they came up with the idea, right? Now, they did that right around 1918, 1917. Hey, those are familiar dates. Now, he was a German. And these Germans, of course, are extremely good at chemistry. That's why we run into the mole, the lovely German word for a pile. And what we look at this, of course, is the Germans were also very good at growing food, which meant they grew people, and they were good at organizing, so they built huge standing armies in Europe. Those standing armies noticed that, of course, hey, I can also use this ammonia to make things like nitrates to make explosives, like nucleic acid and TNT, right? Now, if you got a whole bunch of people, too many people in Europe, and you got a whole lot of weapons, and you don't have enough food, you start to fight over those things. And that's when Germany, of course, initiated World War I with a nice little excuse down there in Yugoslavia, right? If we look at that, of course, it led to one of the most tragic and violent wars that humans have ever seen, where you had mass killing of millions and millions of people because we had far more people and far more explosives, all because of Fritz Haber, right? Now, of course, when we did that, that shows that there's kind of an issue. There's so many people that you need to kill that you need to come up with other processes. Fritz Haber's chemistry and the use of Le Chatelier's principle allowed him to also produce other chemicals like chlorine gas, phosgen. And they released the chlorine gas, which would go out over the enemy if the wind was right. Sometimes they got it wrong and it blew onto themselves. But chlorine gas, of course, and phosgen is an issue because you can see with these British troops, they would go out into the field after one of these gas attacks, chlorine gas attacks would happen. And what they'd find is they'd find soldiers that had stripped themselves bare naked, and they'd actually ripped out their eyes and their armpits and everywhere there was sweat glands because the chlorine gas reacts with the water in the solution of your eye and attacks any mucous membrane. So it burns the lungs and kills you by suffocation. It burns out your eyes and blinds you, and it stings in all your sweat glands, and so they tear at themselves. It's a horrible way to die. And if you didn't die, you spent the rest of your life blind and usually had respiratory problems. It's great. Humans using chemistry for horrible things, right? Now, if we look at this, there are some positives and negatives to this. If we consider the double-edged sword of Fritz Haber's work, he made tons of food, and that food did a great thing. It allowed the world population to go up higher, which was great because if it wasn't for Fritz Haber, about, anywhere to 60 to 70% of the people in class and in our house and in the world today would not be alive. We would starve to death very, very young. So you can thank Fritz Haber for your actual existence because that's the only reason we have enough fertilizer to grow the food to grow our population to what it is today. Negatives, right? All that fertilizer led to too many people and a series of wars, right? And those wars were more destructive because it also had lots of explosives. So, made people, killed people. Hey, it was reaching equilibrium. It's almost like humans and civilization is an equilibrium reaction. Right? Now, other parts of this that are more direct to his life, if you look at Fritz Haber, he had this pretty wife, and she was actually famous for being a very good chemist herself. She of course, understood what Haber was doing, and what she noticed was that he had done a poison gas attack on troops, and that had killed thousands of people in just a few hours. Now, she, being an intelligent person that actually was part of the investigation of all this, recognized how horrible the person was she was married to and that he'd allowed this to happen to humans. And so she shot herself in the heart because she was heartbroken by this. So he loses his beautiful young wife, who was also a genius and likely was part of the reason why he cracked the Haber process, right? On top of that, Germany loses the war, right? Despite all this technological wonders and not caring about trying things that were horrible. And World War II then ensues because of, the reparations process, and they didn't do it too fairly. And so you have all these disgruntled people. And as they do that, the rise of the Nazis allows for a hatred of Jews, which were then used as a scapegoat for the loss of the First World War. And Haber, like most great scientists and academics in Germany, was Jewish. And so he is forced to leave Germany because they're persecuting the Jews in the new Germany, right? On top of that, he couldn't take his whole family with him because it was hard to get permits. And his family was later killed, being Jews, by the Nazis in the death camps using gases like phosgen that he had helped to invent. Ironic. Included with that, he only lived for about 1 year after leaving Germany. They say he died of heart failure. Some say it was a broken heart. One thing's for sure, the stupid burns. Humans took this thing that could have created a lot of harmony in life, which it did, make a lot of food, and turned it into too many people and too many weapons. But, the stupid, it burns. So hopefully you recognize, of course, that chemistry can have an impact on real life. It led to World War I and World War II and all the world wars that ensued after that, because that's how we make all the explosives as well as the food. So it can be used for good or evil. It depends on what you want to do with it, right? Hopefully we'll start doing some more good with it, like, fixing population problems. But when a system comes out of equilibrium, there's too many people colliding, you tend to have wars that decrease the number of people, right? Or diseases show up that affect their food or their bodies. 1918. Oh, Spanish flu. Now, if you look at Fritz Haber, of course, normally we'd be looking at the concentration effects lab at this point, the PCL5 sheet, which are good reviews. You'll notice that he looks a lot like Herr Seeger. Very shiny. Interesting. Now, what we're going to look at now is we're going to look at the concentration effects lab, because it beautifully shows this thing called Le Chatelier's principle. Now, what you want to do is, of course, you want to draw these 5 tubes, and you would do the lab normally in class, but we'll take a look at it together today to get the idea. You can see that this is an equilibrium reaction. It can go both directions. These would be my reactants. These would be my products. And the thing that I should notice is the products make this solution that's called iron thiocyanate. That's what the S is for. And it's red. It's visibly red. That's why we use it, right? Now, key things about this first tube would actually be our standard. It's used for a control group that's used for comparison, right? And when we want to compare this thing, we want to know what it looks like when it's at equilibrium. This tube would have, of course, the iron nitrate and the potassium thiocyanate that would go in, and it would make this stuff called iron thiocyanate ions. And they would be nice and red. So this tube would be a nice deep red, right? What this means is this is a tube number 1, that's at equilibrium. It's making and breaking products and reactants at the same rate, and at equilibrium, it's red, which means it favors making lots of the iron thiocyanate, the red stuff. That's why we use it. You can visibly see the red stuff. In the second tube, there was a change that was made. You would start off with the tube that had the red stuff in it, iron thiocyanate, and then you would add something else. You would add iron nitrate, right? And if we look at that iron nitrate, it's aqueous, and when you drop it in there, the solution would get darker red, which means that we just took this reaction and we shifted it to make more of the red stuff. We shifted it forward because if you consider what we're doing, we're basically adding a reactant. We're adding the iron part. And the iron allows you to make more of the product because it's going to collide more with the other reactants. If you add reactants, if you add it, move away, this will now make more products, right? Oh, the red stuff, the Chatelier. If we look at the next thing that we would do in the third tube, we would add something again, but this time we would add potassium thiocyanate, another reactant, but we would add it as a solid. And when we add it as a solid, a neat thing happens. It shifts to the right, but it gets even darker red, which means we definitely made even more of the iron thiocyanate. You can visibly see it. Now that makes sense because what do? We just added a reactant. These are my reactants. These are my products. If I increase the reactants, they collide more often. So when we add that reactant, though, we use the solid because a solid is more concentrated. There's no solvent in it, right? So that's even more. And if I add more reactant, well, then I'm going to produce and shift it even more to make more product. That's why I draped it red. Hey, the concentration affects it. This lab is called the concentration effects lab. By adding more of the reactants, we're changing the number of reactants, and that produces more product. Le Chatelier, add away. Now, in the fourth tube, there's a really neat thing that happens. We add stuff, but what we added this time, we would add a thing called silver nitrate. Now, the silver nitrate, when you put it into the tube, it turns lighter, and then it can go nice and clear, and it will actually form kind of a white precipitate at the bottom, right? Now, why is it turning clear? Well, it's got two parts to it. The nitrate's just a spectator. You can see it right there. But the silver is what matters. And the silver has a charge of 1+. Hey, who would match up perfectly with a 1 plus? A 1 minus. What this ends up doing is it forms a white precipitate called silver thiocyanate. That forms a solid which takes it out of solution, which means you're decreasing the amount of cyanate ions in solution. Hey, that's a reactant. What I basically did by adding this new thing and precipitating it is I take away the reactants, the thiocyanate. If you take it, it moves towards. And that means it shifts the reaction in the reverse reaction, and it goes clear because if I take away reactants, then it's got to make more reactants. And the only way it can do that is by destroying products. And that means it has to destroy the iron thiocyanate to get more cyanates. Hey, I didn't have enough thiocyanate reactants colliding, so it destroys the red stuff to make more of them. Hey, it's reaching an equilibrium, right? The fifth step of this is pretty cool. What we do this time is we add toothpaste, sodium fluoride, or at least an ingredient in sodium in toothpaste, right? Now, when we do this, this also will turn clear, and it makes a precipitate. Now, why does it do that? Well, if it turns clear, you must be destroying the red stuff, the iron thiocyanate. And that's because, of course, what it does is it basically forms a new precipitate called iron fluoride. It's the iron 3 fluoride, and that is a solid. That comes out of the solution. You're taking it away, which means really what you're doing is you're taking away the iron. And that's because the fluorine has a 1 minus. The sodium's just a spectator. The sodium's just a spectator in this case, right? And what this means is it reduces the number of iron 3 plus ions that are flowing around. And that means that if I, of course, form the iron fluoride, I'm going to take away reactants, and that's going to shift it to the left. And when I do that, of course, it's going to shift it towards. If I take reactants, it shifts towards and makes them, right? This will now make more reactants, more of the iron stuff that was taken away. And if I make more iron, then I have to break more iron thiocyanate. I destroy it. And that's why the red goes away. And you can see a beautiful process of this. Basically, what I'm doing is I'm changing the concentration of the reactants in each of these cases, which can have an impact on the concentration of the product, the red stuff that you can see. Hey, concentration effects. Le Chatelier. You add it, move away. You take it, move towards. It's a simple way of looking at it, but it's really about if I make more collisions on one side, it goes to the other side. If I take away the thing that's colliding, it'll react to make more of the thing I took away. So that keeps colliding. Hey, pretty elegant, right? Now, on top of that, we would normally be doing the equilibrium test, and you'll be getting that this week. And if we look at the big idea of this, today was shooting after the Haber process and understanding basically how it works. Haber was all about figuring out an artificial way, a synthetic way, of turning nitrogen and hydrogen into ammonia. Why did he do that? So that we could have lots of fertilizer and lots of explosives. Benefits of that, made lots of food, lots of people, but this population boom meant that there were too many people and led to World War I, then World War II, and all the wars that faced after that with overpopulation. Now, if you look at this, of course, and apply these ideas to not just chemistry but beyond, you can notice that this skyrocketing means there's too many people colliding. And if too many people collide, you're more likely to have collisions called wars. Oh, or, infectious diseases you can't control because there's too much of a population. Hey, you can learn something from chemistry if you pay attention.